In this video, we will discuss how to go about designing a simple structure for tensile loading. We will use tensile strength, a specified tensile load, and a safety factor to design a specimen with an appropriate width and thickness. And this is one step toward the project where we're going to test these specimens during class. On the engineering content website, you will find the following information. We talk about a sigma, which is the symbol given here, as being equal to force divided by area. Now, this is for normal loading on a bar. It's often called uniaxial loading. And we won't go into many of the details that will be covered in further engineering courses. But what we can think about here is having a force on either side of a member or bar and having that acting over some cross-sectional area and then having some stress distributed across that area. Now, for this problem, what we are going to do is take this same equation, which we normally use for cases that are not breaking in the structures that you might see around us every day, and liken it to what you have when there is a force that's being applied to cause the sample to break under tension over a given area, as seen here, and then write that as an ultimate tensile strength, often given by S sub U. Same units where we have newtons for the force, we have meters squared for the cross-sectional area, and we have newtons per meter squared, or pascals if we're dealing with SI units. And in mechanical, civil, or other engineering fields, what you'll often see is these ultimate tensile strengths not reported in terms of pascals, but out of convenience, they're reported in megapascals. And 1 million pascals, or 10 to the 6 pascals, is 1 megapascal. Now, let's go on and do a few more calculations to demonstrate how we might design a tensile structure to be able to handle a particular load. As we've discussed in the notes that you've seen on the website, we have the ability to present or talk about what a ultimate tensile strength might be. So in a previous test in the lab, we took a piece of paper and that you're going to be using, and we calculated or estimated a tensile strength, an ultimate tensile strength of 33 megapascals. Now, this is not a 100% precise number. There's a number of factors that can go into the uncertainty that guides this number being high or low. Humidity, temperature, moisture that might be absorbed in the paper, even differences in one sample to another. And also, paper is often stronger in one direction than it is another. This happens, these samples that you'll be using are stronger in the direction that we will be pulling, or the length of the samples. Now, let's say we want our support for which we're designing to handle a particular load, let's say 50 newtons. And on top of that, we want to have a safety factor of 1.5. So this safety factor might be appropriate for an aerospace structure, and you can see a few notes about safety factors on the web page. Well, we need to figure out what the cross-sectional area is going to be to support this load with a safety factor. Now, what we might be able to think about without even doing any calculations is that if you make a piece of material thicker, it's going to be able to support more force and tension or in compression. If you take a large stick or branch or trunk from a tree, you know that the larger the diameter it is, the more force it's going to be able to handle. So what we want to do is design a cross-sectional area that will appropriately handle the force that we're discussing here. Well, what do we do? First, we might think about what is the actual force that would occur at break? And it's not the 50 newtons that we're specifying here, but it's the safety factor times that amount. So that would come out to be 75 newtons for this particular case, 1.5 times 50. Then we talk about that force at break, and we divide it by some appropriate cross-sectional area, and we reconfigure using just simple algebra what that cross-sectional area should be. So we can say that the force at break divided by the ultimate tensile strength, which we've calculated or we've measured previously, will be able to give us the designed cross-sectional area that might be appropriate for this problem. So we then have our safety factor times the designed, the force for which we're designing, divided by the ultimate tensile strength, and we can write that with some numbers. And let me point out that in mechanics and materials, which I teach, and in other engineering courses, I think it's often very useful to write your responses out in algebraic form, and then when it's appropriate, you plug in the numbers with the appropriate units, as you see here. So just building on what we just wrote, we have this equation for the cross-sectional area. We then go ahead and we do a little bit further analysis here with the dimensions. So we know that we have the 75 newtons in the numerator, and we can say, oh, well, we had megapascals, and megapascals or 1 megapascal is 1,000,000 pascals, so we can write it out like here. And then we go ahead and we say, oh, I can convert pascals to newtons per meter squared, as you see here. And you've probably done this before. I find, though, that often when we're moving quickly and we're like, oh, I don't really need to think about units because I just want to get the answer, that we skip this step. And it makes a difference, at least in mechanics and materials, which I often teach. So now what we see is we can cancel out further the newtons and newtons, and we're left with 1 over meters squared in the denominator, which means that it will be meters squared in the numerator, and we can calculate what the cross-sectional area will be numerically. Now, what does this really look like? We're talking about cross-sectional area, and maybe it's a good idea just to revisit briefly what that means. We have a cross-sectional area of a sample that we're putting in a tensile specimen, so that area might be given here, and then we have width and thickness, okay, of that particular sample. Now, when we're doing this design problem in the course, or just today's session, what we see is we have sheets that have 0.1 millimeter thickness, but you can use multiple sheets. So let's say you want to get to a higher force, we can stack these sheets of paper, say 3 sheets of them, and that makes the effective thickness 3 times that 0.1 millimeters. So we get to a thickness of 0.3 millimeters. And then what we say, if we're looking at the cross-sectional area, is we have our thickness. We want to figure out our width. So our width is just going to be that cross-sectional area that we calculated out over here divided by that thickness, and we get the appropriate width. Now, one thing that you want to make sure that you do when you're calculating out the appropriate thickness and width is take a look at the sample that you're given, or the samples, the multiple sheets of paper and their cross-sectional area. Make sure that you can get the thickness that you want. Make sure that you can get the width that you want. These samples, we can cut them down, but it's very hard to add material to make them wider. So as you're designing and calculating out the appropriate dimensions, the cross-sectional area, the width, the thickness for your sample that's going to be under load, keep these factors in mind. Thank you very much.